In a previous video, we saw an annuity where the payments being made to a person were a regular amount. But if a person makes an investment and then uses that money in their retirement, what they may wish to have is that the payment that they get increases so that it matches inflation over a period of time. So in this example, we're having a look at an annuity where the payment being made to the person is increasing at a certain percentage each year. Let's have a look at a particular example, and it's suggested that what you do is read the example, then pause and see if you can look at the key parts of the question that we need to actually take into account to work out how long this annuity will last for. So let's highlight the key parts of this problem that we're going to use to solve the question. And the key question is shown in red, and that is how many years will this account be able to provide for us if we're getting $40,000 per year. And you'll notice in the brown writing at the bottom, the other bit, which is that the amount is increasing by 3%. So let's use a sequence to solve this problem. In other words, Tn can represent the amount in the account after any number of years. So initially, we have $500,000 in the account, which is after 0 years. Now what happens is that increases by 4%. And the way we express that is we say that after any number of years, the amount in the next year's account, in other words, Tn plus 1, is going to be the same as what we had. That's why it's multiplied by 1, and a little bit extra. And that little bit extra is 4%. We express that as 4 over 100. So our sequence rule is almost complete. You'll notice on the right hand side of our rule there we've left some dots because we're going to subtract some money each year. So basically the way this account is working is we're adding interest, but we're taking away $40,000 or a little bit more over each year to make sure that we have a regular income. So let's see how we can express that using the rule. Well, in the first instance, in other words after 1 year, the amount in the account will be whatever T0 was, increased by 4%, and then we take away 40,000 at the end of that first year. At the end of the next year, which will be T2, it's the same idea. That's T1 multiplied by 1, so we get the same amount back, plus a little bit extra, which is 4% or 4 over 100. Now when we take away our $40,000, we're going to increase that by 3%. So we write that as 1.03. So we can see that final figure on the very right hand side of our rule is going to be changing all the time. We're going to be multiplying by 1.03 each year. So how do we express that in a form that we can put into a calculator which is going to be consistent year after year? Well, let's have a look again at the first year, and what we'll do is we'll multiply our $40,000 by 1.03 to the power 0. Now we know that anything to the power 0 is just equal to 1. So effectively we're just multiplying 40,000 by 1. The next year we're multiplying 40,000 by 1.03, but we'll express that to the power 1 because anything to the power 1 is just itself. And the reason why we're doing this is so that we can tie up those values in red with something else in our formula. You'll notice that in the first line, the 0 for the 1.03, in other words the index, matches the 0 at the beginning of the rule, which is T0. The 1.03 to the power 1, which is shown in red, that also matches the T1 at the beginning of the rule. So we can summarize our rule as follows. We can say that the amount in the account at any year is equal to the amount in the previous year. We have our percentage increase, which is represented by 1 plus 4 over 100. And then we take away 40,000 multiplied by 1.03 to the power n. And the reason why it's to the power n is because it matches the number at the front of our formula just after the equals sign. So what we'll do now is we'll use the Casio Classpad to solve this using the sequence program. So we'll enter our sequence into that part of the program, and you can see here on the screen we've already done that. And what we'll need to do is just look to the right hand side as well to see the 40,000 multiplied by 1.03 to the power n. And now what we'll do is we'll set up a table of values to investigate how long this account does last for. Now being for retirement, it probably lasts for 20 to 30 years because that's most likely what this question's about, an investment of money for a person's retirement. So looking at the table of values, we start off at $500,000 after 0 years, and if we scroll down that table we can see on the right hand side the amount that's in the account shown in blue writing. Now that is in scientific notation initially, but as we go down we can see that after 14 years the amount's negative. That means that basically the account's run out. So we get 13 years of full payments, and the 14th year there will be a partial payment, but it won't be the full amount that we'd expect. So to summarise that, we get 13 years of full payments, which covers the expectation of $40,000 increasing by 3% each year. But in the 14th year, what we do is we get the amount in the account at the end of 13 years plus the interest. Now from our table we saw that was $46,377.58. Now the interest is 4% in terms of how much the account increases by compounded annually. So we multiply that $46,377 by 1.04, and the amount that we get, which we'll receive in the 14th year, is $48,232.68.